Have you ever watched a jet streak across the sky and wondered, what makes that thing go? It's not magic, though it might seem like it. It's engineering at its finest. At the core of a jet engine is a surprisingly simple principle. Suck in air, squeeze it tight, and blast it out the back. This creates a powerful thrust that propels the aircraft forward. Think of it like blowing up a balloon and then letting it go. The air rushing out the back sends the balloon flying. That's essentially what a jet engine does, but on a much larger and more controlled scale. It's all about creating a controlled explosion that generates incredible power. But how does a jet engine actually achieve this? That's where things get really interesting. We're about to dive into the heart of the beast and explore the intricate dance of turbines, combustion, and exhaust that makes jet propulsion possible. Get ready for a wild ride. The real workhorse of a jet engine is the turbine. This spinning marvel is responsible for compressing the incoming air and then harnessing the energy of the ignited fuel to generate thrust. Imagine a giant fan, but instead of just moving air, it's compressing it to incredible pressures. Here's how it works. Air enters the engine and is met by a series of spinning blades called the compressor. These blades force the air into a smaller and smaller space, increasing its pressure. This compressed air is then mixed with fuel and ignited in the combustion chamber. The resulting explosion forces hot gases through another set of turbine blades, spinning them like a windmill in a hurricane. This spinning motion powers the compressor at the front of the engine, keeping the whole cycle going. Finally, the hot gases are blasted out the back of the engine, creating the powerful thrust that propels the aircraft forward. It's a beautiful symphony of controlled chaos, a delicate balance of pressure, temperature, and airflow, and it all happens thousands of times per minute, propelling us across the skies at incredible speeds. Now, imagine trying to control something as powerful as a jet engine with just your bare hands. Impossible, right? That's where hydraulics come in. These systems use pressurized fluids to amplify force, allowing us to control enormous machines with incredible precision. Think of squeezing one end of a toothpaste tube. The pressure you apply travels through the toothpaste and forces it out the other end. Hydraulics work in a similar way, but instead of toothpaste, they use special fluids that don't compress easily. In a jet engine, hydraulics control everything from the angle of the turbine blades to the movement of the aircraft's control surfaces. They're the invisible muscles that make these complex machines move with grace and precision. But hydraulics aren't limited to aviation. They're used in countless applications, from construction equipment to car brakes. They're a testament to the power of simple principles applied in ingenious ways. Section 4. Controlled chaos, combustion, and flight. We've talked about turbines and hydraulics, but what about the heart of the matter, the combustion that makes it all possible? Inside the combustion chamber of a jet engine, a carefully controlled explosion is taking place thousands of times per minute. Fuel is injected into the compressed air, and a spark ignites the mixture. This isn't your everyday campfire, though. The temperatures inside the combustion chamber can reach thousands of degrees, hot enough to melt metal. But the engine is designed to withstand these extreme conditions, channeling the explosive force of combustion into useful thrust. The key to this controlled chaos is precise engineering. The shape of the combustion chamber, the angle of the fuel injectors, even the composition of the fuel itself, all of these factors play a crucial role in ensuring efficient and powerful combustion. It's a delicate dance of fire and air, a testament to human ingenuity and our ability to harness the forces of nature for our own purposes. Section 5. Flowing forces, from electrons to hydraulic fluid. Powering these complex systems requires a different kind of flow electricity. Electrons zipping through wires provide the energy for everything from the engine's control systems to the aircraft's navigation equipment. But electricity isn't the only thing flowing through a jet engine. We've already talked about hydraulic fluids, but their importance bears repeating. These fluids, often oil-based, are the lifeblood of the hydraulic systems that control the engine and the aircraft. They flow through intricate networks of pipes and valves, transmitting force and motion with incredible precision. Then there's the flow of air, the very essence of a jet engine. From the moment it enters the engine until it's blasted out the back, air is constantly moving, being compressed, heated, and expanded to generate thrust. Understanding these flows of electrons, fluids, and air is key to understanding the intricate workings of a jet engine. It's a symphony of motion, a testament to the power of harnessing natural forces for human endeavors. Section 6. A glimpse into the future. Blueprints of innovation. As we push the boundaries of technology, our machines become ever more complex. Imagine a blueprint for a futuristic laser space gun, its intricate design hinting at the awesome power it possesses. This weapon might utilize principles we've discussed: whirling plasma, contained within magnetic fields, to generate a focused energy beam. Electric arc devices could provide the initial energy burst, while advanced hydraulics control the weapon's aim with pinpoint accuracy. While this is just an example, it highlights how the principles we see in jet engines, controlled explosions, fluid dynamics, and electrical systems, can be applied to create technologies that seem ripped from the pages of science fiction. The future of engineering is about pushing these boundaries, exploring new frontiers of possibility, and building the machines of tomorrow, one innovation at a time.